Welcome to the short version of my lecture, Fermat's method of integration and the hyperbolic curve. Okay. So Pierre de Fermat tried to calculate the area underneath the curve y equals x to the n, and he did so by making these rectangles, except what he would do, he would go backwards. So the first rectangle was at a point A. So we're trying to find the area underneath the curve from the origin to A. And the edge of the next rectangle would be at x equals AR, and the edge of the next rectangle would be at x equals AR squared, and the next rectangle would be at, the edge of the next rectangle would be at AR cubed. So, for instance, if you want to calculate the base of this rectangle, you would do A minus AR, right? A minus AR. And then to calculate the area, sorry, it would be A minus AR, that's AR. To calculate the area, then, we'd multiply this by A to the n, right? And to calculate the area of the next rectangle, we would take A times R minus this, AR squared, so that's the base, and multiplied by AR to the n, right? So when we, and this goes on forever and ever, it's an infinite geometric series. So we can make the sum, we can make the area the sum of all of these rectangles and convert it into an infinite geometric series. And remember, in an infinite geometric series, like 1 plus t squared plus t to the third forever and ever equals 1 over 1 minus t. So if we replace t here by r to the power of n plus 1, okay, we get that. And we can multiply this out and get this. We can factor a 1 minus r, and then we would get this, right? Okay, and then on the denominator. So these would cancel out, and we would finally get this. And as r goes to 1, we would get this expression, which is, of course, the expression for the integral for the curve y equals x to the n. Okay, so that's what Fermat did, although it doesn't work for our hyperbola y equals x to the negative 1, because if we put in a negative 1 for n, we get this expression, which is a big no. We can't do that. We can't have 0 as the denominator. Okay. One of Fermat's contemporaries noticed, however, that when we do this technique and calculate the area of these rectangles to add up to the hyperbolic curves, every rectangle has an equal area. This means that as the distance grows geometrically, the area grows arithmetically. So the area and the distance has a logarithmic relationship. In other words, the area underneath the hyperbolic curve, y equals 1 over x, from a fixed point to z equals log z. The only question now is, what is the base?